G. Oh, I can't. Okay, welcome to 240. So, well, first, do we have questions or so? Okay, so we're in the midst of talking about device models for MOS transistors that are for design. And last time we looked at, in particular, two things that one of them in particular is very important. We looked at this V-star business, or we looked at also at, and that is related to efficiency of transistor GM over ID. Right? GM over ID is a very good figure of merit because it really relates two of the most important parameters that we have when we are designing circuits. GM is what we want out of the transistor, that's why we put it there. And ID, of course, is the price we are going to have to pay. And they are related, so this V-star business as follows: 2ID over GM is equal to this V star. Now, really, what we care about and so on is this GM over ID, right? But GM over ID has sort of strange units, and aside from this efficiency in other direct circuits, meaning so we much rather use this V star. Now, there is often a confusion about sort of the meaning and status of this V star. And the reason is that for the square law model, V star and VD set are exactly the same thing. So why don't I call this just V star? Well, the reason is that this really is a definition. This is always true. It doesn't matter at all whether this is a crooked transistor with God knows what strange characteristic, or a transistor that by miracle actually adheres to the square law equation. And so if you rely on this being VD set, you get errors because when you believe that, then you also believe that the ID in saturation is equal to 1/2 mu Cox W1L VD sat square, right? That's what you believe. Well, if you use this V star in here, you get the wrong value, or if you use this VD set for here, then you get the wrong ratio for GM over ID. So that's why we have to be very careful. It is sort of like an approximation of VD set, but it's only an approximation of VD set. Whereas this business here, I mean, this is the definition, is always accurate, totally independent. There is no, you'll never have this problem that, well, you know, my calculations are going to be off from SPICE because fundamentally I make an error. Fundamentally, you do not make an error with this thing. And the errors are going to be because SPICE uses 64-bit floating point numbers and you use 2 digits, right? Or more typically, you miss or do not accurately model a parasitic in your circuit, especially a capacitance that SPICE will. And so then you get some discrepancies there still. But this stuff here, it's going to be dead on. But because we define it that way, right? So the other thing we talked about was charges or capacitors. There are really two things to this capacitor story. One of them is that they're really important because they are also affecting circuit performance in a very, very significant, profound way. Right? They say how fast things go. They say how much noise we get, and so on and so forth. They really matter. But the other thing is that they're very difficult to, just like other stuff like this equation, so they're just very difficult to track. Right? Equations are very complicated. And we talked briefly about this issue of charge conservation, that we really can't use these capacitors in the first place to model a device that has more than 2 terminals, right? And and consequently hand models are inherently approximations. Of course, I could try to sort of pull the same trick, define something that then is always right, but I'm not going to do that here because I don't know how to make this useful for design. This thing is going to turn out to be extremely useful for design. That's why we do this. But here I really don't know. I don't know how to pull a trick. I mean, certainly what is important is like this 2/3 WL Cox, right? That kind of equation, and you're going to estimate CGS about using this equation. Likewise, it's important to realize that, especially in deep submicron technology, the junction capacitors, they are often very significant. So don't leave them out. And if you don't want to calculate them by hand, which is a little bit tedious, then do yourselves the favor that if you define a transistor in SPICE, right, and then what is it? Drain, gate, source, bulk, and then L something, W something, right? And then also specify a source equals a drain equals something, and same thing for P, the perimeter of the source. So you're familiar with that, right? Okay. Specify those, because the default in SPICE, or in most versions of SPICE anyways, is that they're all 0. And you're really fooling yourselves if you do that. A very common mistake in design. Well, first I sort of I ignore all these second order effects. Well, these things are not going to be second order very often. And if you don't include these parasitics in your circuit, then SPICE will say, well, everything goes just fine. It's actually even faster than you need it. But then when you stick all of that stuff in, of course, the circuit's not going to meet specs. And you have to start from scratch designing it again. So PD, there is also PD. Right? Okay. So so figures of merit is, I guess, a good sort of mantra for transistor models. Here is another one that is very important. And that is a high frequency figure of merit. Up to now, we really didn't look at the frequency response at all. And there are a couple. One of them is physically kind of a strange thing, and that is the unity gain, the unity current gain bandwidth of the transistor. What is it really? Well, if we have a MOSFET, and we are driving it with a current source like this, then of course that's the CGS, right, that this current is going to flow into. I'm not proposing that the MOSFET is going to have a leaky gate suddenly. Okay, I'm not interested in that effect, fortunately yet. Right? And then of course it's going to produce a current ID at its output. So there is going to be a current I source that flows into this thing as a function of frequency, and there is going to be a current ID that flows into the drain, right? And the current gain AI is then equal to ID over I source, right? Much like we can define a voltage gain, of course we can define this current gain. Is it interesting? Well, we'll see, right? Certainly we can define it. Now, if you actually want to measure it, you need a little bit more complicated than that. Right? You need to also have some biasing source and so on. But in principle, you can do that. And if we were to plot this AI, which is a function of frequency, as a function of frequency, then it would presumably, because of finite output impedance, would something like this at low frequency, and then it will roll off, right? And at some point, so this is frequency, and I plotted this on a log scale. At some point, this drops off to unity, and we call this here the transit frequency ft, which is also equal to, of course, omega t over 2 pi. Now, this is a very simple circuit. If you solve it, you actually will find that this omega t is equal to to Gm, the transconductance of this device, divided by the capacitances, CGS, right? Obviously, the current flows into the CGS, and there is also CGD that also is grounded, so that adds here. Okay. So it's a useful figure of merit. Well, it kind of says something about sort of the transistor's own SIP versus the load it presents, right? If the transistor doesn't even produce as much current as its drain as it needs to charge its gate capacitance, it's kind of probably not that useful anymore, right? In some ways, of course, we could say, well, what do I care? I care about the load out here and this here. That's the guy who's driving me, right? Perhaps off chip or so. This guy's problem. Well, very often we will have a feedback loop, for example. And then we very, very well can load our amplifiers with their own capacitances. So it's not too surprising it will not be too surprising if afterwards when we derive design equations for all sorts of circuits, we'll find that this omega t actually pops up more often than we maybe might think. So even though this current gain business looks a little bit strange, when we design circuits, you'll find that it's actually a very useful thing. Okay, so now again, if you can use a little more zoom, please. Okay. Now, if we assume that we had a square law model, then of course we can find an expression for GM and expressions for CGS and so on, and then we'll find that this omega t is approximately equal to the mobility times VDZ over L square. Here we have it. That's why. This is why we want to have small transistors. Obviously, omega t, this bandwidth, right, being high, infinite is a good thing. Consequently, L should be small, and heck, if it appears with square, then that's really important. That's why. This is why. This simple equation tells us why we are craving always forever smaller transistors and why that's a good thing. Why things keep getting faster, right? That's what this is. Okay, so we will be using this most of the time, and we'll find that in the end, actually, very often that's an important parameter in our circuits. There are other sort of high-frequency figures of merit for transistors. One that physically kind of makes more sense is the unity power gain of the transistor, where we need a certain amount of power that flows into the gate, and there is some amount of power that comes out the other end at the drain end again, and that ratio better be larger than 1, otherwise we could use a passive attenuator, right? And so this is an expression that sort of captures that. A little bit more complicated because now it includes, and if we make the gate material resistive, well, the signal never really reaches the gate of the transistor, and we will have lots of dissipation there. So if you're interested in that, this figure of merit is used more often at high frequency. This is a reference that has a nice and simple discussion of that. Okay. So now in this slide I plot our figure of merit. That's this FT. That of course is in gigahertz now, and this is for an NMOS transistor as a function of VDS, right? So or VGS actually. Again, around here somewhere we have the threshold voltage. So down here we are in weak inversion. Up here we are in strong inversion. Also shown in that same slide now is the sort of the V star efficiency, GM over ID, right? And that's also plotted for N-channel and P-channel transistor, and it says that, as we've seen, that we really would like to use small VGS. We would like to run the transistor in weak inversion or close to weak inversion to get high current efficiency. Well, if we want to get high speed, apparently just the opposite's the case, right? Another insurance for analog circuit designer. You can't just blindly go here or go there. You're not going to do very well with that. Right. There is another interesting thing in this graph, and that is that the GM over ID apparently doesn't matter at all whether we have NMOS or PMOS, or it turns out also it doesn't matter whether we have a 1 micron or 10th micron processor. So this pretty much, to a large extent, this is physics. This is sort of fundamental physics. It doesn't depend very much on. Now, especially, interestingly enough, it doesn't depend on NMOS or PMOS. So if you're talking about just efficiency in general, if we talk about DC stuff, then perhaps we could use the PMOS just as well as the NMOS. If we talk about speed, that's no longer so. This is the NMOS, and this is the PMOS. So the PMOS has about half, or something like that, the FT of the NMOS device. So in practice, of course, we always, if we want to be really fast, well, we want to be here. If we want to be really low power, we want to be there. And if we want to be both, we are kind of stuck, right? I said already, it depends on the technology, and we see that here, right? So here is shown FT as a function of VGS again. For different channel lengths, different processes, in fact, it's always the minimum channel length for the respective technology. And we see the 0.18 micron has by far the highest FT. We also see that we really get a large boost here for sort of modest values of VGS minus VTH. And then sort of the benefit starts running out. Makes perfect sense, because up here we really just get all these velocity saturation effects to the nth power, and consequently kind of are running out of steam. But we see that, it looks like, heck, 0.25 micron, and then it's not even a factor 2, right? Square root of 2, we go to 0.18. Big deal, right? Well, yeah, it's a really big deal, right? Really makes a big difference. And the reason, of course, is that square in our equation, 1 over L squared. Right? Now, one question is that, well, when we trade off here, sort of what is the right trade-off? What are reasonable values for VGS minus VTH where we want to run our transistors at? And the next slide shows that also. Right, if we make VGS minus VTH, which is approximately, but only very approximately equal to V star, right? If we make that very small, then we are in weak inversion. We have good current efficiency, but we have slow speed, and then over here we get to very high speed. Well, one way to sort of trade them off is we want both. So we want the product to be maximized. And so this actually just plots the product of these two numbers. Has no physical meaning, I think. At least I wouldn't know of it. But so this would be kind of an overall device figure of merit, right? And it says that we should be somewhere between 1 and 200 millivolts, at least for the short channel devices. And it actually has come down, right? In a half micron technology, the peak, we cannot see it very well on this scale, but there the peak was perhaps 100 millivolts higher. So that's actually a good thing, right? As supply voltages, of course, shrink also, as transistor dimensions shrink, at least we need less voltage to run our transistors, and we still can go faster. Okay, and more current efficiency. Actually, the current efficiency increases, right? Because we are moving down here. And the speed, we more than retain, because the reduction going in this direction normally would make things slower, but the FT increases so incredibly much that this shift is more than compensated.
Question?
Yeah.
Yeah. Go to the last slide. So the device figure of merit is FT times the GM over the ID, right?
Right.
And then a few slides before, we have the omega t equals to mu times the VDZ divided by the L square. And then if if we use this omega t times the GM divided by ID, we can actually use the VD set and then cancel out the GM over ID, isn't it? Because VD set is the approximation of V star.
Yeah. I mean, if you use the square law model, I have now even forgotten this because it's been such a long time that the square law model was useful for me in design that I kind of forgotten what it did. But yes, of course. Yeah. Well, so we would basically put omega t times GM over ID, right? Okay, so that is actually equal to GM square over CGS times ID. And GM square is equal, what is it, 2 mu Cox W over L times ID, something like that, right? Yeah. And then CGS times ID. And then so we have mu Cox W over this one here is, forget about the 2/3, right? We're generous. This is W times L, and we have another L here times, well now I'm, yeah, times Cox. So, oh yeah, so yeah, you're right. Yeah, of course, yeah, just the VD set drops out. So it's mu over L square.
It just depends on the mobility and L.
And L, yeah. That's right. If we had square law. Now, of course, the real transistor is more complicated, but yeah, it seems to be that yeah, not too surprisingly, as we go, we get shorter L, obviously, right? And mu, well, is this complicated function of VGS actually. So I guess what I probably could have done is I could have multiplied this figure of merit here with L squared, right? And then I could have said, well, this is the value of the mobility as a function of VGS. We would have looked at this and said, well, what good is this thing for, right? But you're right, they are connected like that. Oh, yeah. So, but it's not really the mobility that we are. Yeah, right. There is something more to it. It's not really the mobility that we are interested in here. Is it even true that the mobility is peak here? Whatever, right? Whatever beats me. Anyways, here are all sorts of physical parameters that we multiply together and so on. So intuitively, this makes sense. If we again go to the square law approximations, it's going to be very hard to make sure that our interpretations are really correct. But it's a good idea to sort of muse about this thing and figure out how things are connected, because ultimately that's what we're doing all the time when we do design. Okay, are there other things we want to look at? Okay, so the next thing we want to look at, it's kind of going back to DC again, look at the output resistance of transistors. And that's the square law model, I mean this level 1 model, of course has an opinion about that too, and one that is not too accurate. So in that case, what we are really doing is we are looking at the, and we are keeping VGS constant now this time, and we are looking at the current ID, that if this good current source should be constant, and so we look at ID versus VDS, and so first we are in triode region, then it looks something like that in saturation, right? So this, okay, and then our out is simply 1 over this slope, right, of this line. So we can then, just by inspection, make a plot of our out, and so here we get something sort of modest, and then here it's pretty high, right? And so this somehow jumps. I don't know. jumps up something like that, and then we have some kind of a kink, and so this is somehow this is our out, and this is where we go into saturation, and over there we are in triode region, right? That's the opinion of the square law model. What do you think about it? Okay, so so that's probably not what's happening in the device, right? So lacking a real device here, I ran SPICE and evaluated or out for various VDS for both NMOS and PMOS, and well, it looks remotely similar. Or out indeed is very low in the triode region. Well, no big surprise, and then it shoots way up. It's not exactly a flat, constant thing in saturation. Also, the transition region. Never mind here. This is 1.5 volts, right? When we finally reach this peak. Right? And then, interesting enough, in particular for the NMOS device, it starts rolling off again. Anybody has an idea why it rolls off? Yeah. Impact ionization. Okay, so so what's happening is that so here we have the drain, here we have the source. As we crank up VDS, the electrical field here gets larger and larger, and the speed, the velocity of the carriers also get larger and larger. And when they arrive at the drain, they have a lot of energy, and they crash into I guess the atoms there, and they yank out an extra electron, and that an extra electron hole pair, and 1/2 of it disappears in the substrate, and the other half of it goes into the drain. At net, this produces an extra drain current. It's like if we had the transistor and we have its normal ID, but then in addition we now have an additional impact ionization current that runs into the substrate. And as we crank up VDS, this one gets bigger and bigger. And it's particularly a problem for the electrons because somehow they have more energy. Okay. So that's the reason why, after things sort of get so good, suddenly they get bad again. And of course, technologies are sort of designed and transistors engineered that this occurs somewhere as close as possible, or actually beyond the supply voltage. So for the PMOS, that's pretty okay. For the NMOS, well, this is 3 volts. So definitely, if we put the full 3 volts, the full supply across our transistors, the R-out's going to suffer. Okay. So, well, anyways, I mean, go and describe this with lambda, right? I mean, forget it. It's lambda business, just not very useful. Another issue with R-out is that it actually varies all over the place. Here I've made a nominal fast. I guess this is fast, right? No, this is slow, and this is fast. I just ran those simulations, right, with the different types of devices, and I found that the R-out varies by more than a factor of 2, right, in both ways. So it's also not exactly something to rely on, right? We better don't build circuits that work for R-out 40 k ohm, but they wouldn't work for R-out 80 k ohm, and they wouldn't work for R-out 20. Rather, what we will design is circuits that work for any R-out that's larger than 20. Right? The other thing is that R-out is really not that convenient a parameter because it depends on the bias conditions and so on. A much better thing to look at is the open loop gain AV0. And we'll find that give or take a little bit, that sort of goes with channel lengths. And so if we want to get that's substantially larger, then we need to use a different channel length. So in other words, we can kind of make correspondences between channel lengths and the gain that we can get out of just a single transistor. And again, I've shown here the circuit on how to extract that. It's not always trivial to figure out what is something like the open loop gain or so, right? In SPICE we have to bias the thing, right? And sometimes what helps and what I'm doing here is I actually use a feedback loop. I do not try to set the right VGS, but I'm actually using a feedback loop to set the VGS. And that, of course, is very easy in SPICE because amplifiers, they sort of come free, right? They have them. They're much better ones than we ever could build in an IC, for that matter. One thing, be very careful if you use an ideal amplifier in SPICE. Do not make its gain unnecessarily large. If you do so, you may have convergence problems. Okay, so here, again, I did have to choose a certain V star. If you use a little bit less zoom, please. Hey-ho. Okay, well, this is now a little bit too much. Yeah, okay, well, I wish I had a button here. Okay, so this is about 200 millivolts, right? And just a little more zoom, please. Thank you. So here is again VDS, and I guess this is a PMOS. And this is an NMOS for the nominal, slow, and fast, I guess. And so we can see for a well, let's say we ended up with nominal parameters for an N-channel device, minimum channel length. We can get a gain of about, this is 60 here, an open loop gain of about 60 out of just this N-channel device. Of course, if we ended up with the slope, with the fast parameters, or worst case, then it would be a little bit less than that, but it still would be respectable. Even with my slanted line, it would be still 45. Is this realistic? Should we expect to suck a gain of 45 out of a single transistor? Why not? I mean, it says so. Yeah? You have an idea on your mind.
Probably there is.
Okay. In a real amplifier, if we look back here, I gave it an ideal current source load, right? In reality, that would be a PMOS, and so that would lower things, yes. But even then, I mean, the biggest problem actually is, look at this. This works for VDS equals 2 volts. So we build an amplifier, and let's for a moment even be generous and assume that somebody gave us ideal current sources. It would be nice, right? And this is therefore the output, the out. And in order to have that peak gain, we have to define that the output is 2 volts. Do you think you will sell many of these amplifiers? Not very useful. First of all, most of the time, VDS actually varies all over the place. Here it's the output of the circuit. Even in a cascode, it may vary a little bit, and more importantly, it's certainly not going to be 2 volts all the time, right? Because that would be 2/3 of our supply voltage. Right? So the trouble is that the VDS we are willing to give this thing, right? V star, this translates into V star is equal to 200 millivolts, right? Well, V star sort of again gives us this idea of sort of VD sat. So we ought to get into a high gain or high or out region when VDS is at least 200 millivolts. Let's be generous. We'll see. We need to do a little bit extra, but maybe 300 millivolts. Well, if we go to 300 millivolts, we are here. And now, the gain is 15, right? And then if we go over here, the maximum voltage we can have across, it's just just over 3 volts, 3.1 volts. Right? So, so individual transistors, they perhaps can give pretty impressive gain, but if we really want, so the way we use them, it's not that great. Right? One thing that does help a lot is if we increase the channel length, right? Mucking around this GM over ID will change it a little bit, but changing the channel length has an even more significant impact. And one thing that you will often see is whatever the minimum channel length is of the transistor in the technology that you're using, let's say 0.13 micron. If you increase the channel length by just a tad bit to, let's say, 0.2 micron or so, or 0.18 or so, the R out, or the gain, the achievable gain of the transistor increases dramatically. So if you need gain, then you usually want to use a little bit longer than the minimum channel length. Using much longer would still help, not quite as much anymore, but then of course we have this FT business, right? And so very often we don't want to use really long channel lengths because they are dogs otherwise, right? So here, if we again look at 300 millivolts, now we are at the almost 30, maybe 26 or so. Right. I guess I better would have plotted this on a different scale, right? Who cares that this peak here is, believe it or not, on a whopping 260? Okay, irrelevant, right? Okay. And even at 200 millivolts, we still can get some gain of, here it's about 8. Yeah, the scale of this slide is really wrong. And I pointed out here, and I admitted that the scale of this slide is wrong. So in your homeworks and in your projects and in your whatever else you're going to do, you're always going to use the right scale. Okay? Agreed. Okay, technology trend again. Here, same business for minimum channel length devices over a bunch of technologies. And now, so this is GMRO, so this is AV0. And now, heck, finally the 0.5 micron is the winner. Right, and 0.18. Well, it's not that much gain, right? If we want to have a VDS of only 300 millivolts, for example, then well, a gain of about 10 apparently. And here it's just about 26 or 27, like we had on the other slide. Even though this is a student of mine with this one, the other ones I ran it myself. Now again, sort of. Up here, you know, that's sort of nice. 1 volt, 1.5 volts across the device. Not very practical, right? Actually, how? Yeah, I guess in 0.18 micron we still can have 1.5 volts. So I zoomed in here a little bit just to up to 400 millivolts, and sort of we can see, right? So in our 0.35 micron technology, if we want to have a VDS min of about, let's say, 250 millivolts or so, then the gain we can get out of that transistor, sort of 12, 14, somewhere around there. Right? And then again, as you pointed out, we're also going to have a load that also is going to have finite on. And so we may be getting half that. So if we want to get a bit of gain, we need a lot of stages. Right? Plus, of course, if we really want gain, we probably are going to use just a tad longer than the minimum channel length. Right. Okay. This slide here comes a little bit out of sequence, perhaps. It talks about the saturation voltage versus V star. And the reason it's here is that that in the past, when I didn't, especially before I didn't have this V star, I just called it VD sat. People were always confused. And the confusion really is that VD sat is extremely poorly defined. It has a ton of meanings, and none of them is extremely well defined. One of them is that it's the minimum VDS that I need so that I suddenly and miraculously get high output impedance. Well, we've seen that minimum just plain doesn't exist, so speak of a poor definition, right? The other thing is that this VD set is VGS minus VTH. It also is the proportionality factor that, when squared, tells us how much current we get at the drain if the transistor in saturation. And it's a whole sorts of other things, right? Well, in real transistors, it just diverges. These are all different numbers, right? And so V star is, in a way, just one meaning of all these. It's just 2ID over GM, and it's nothing of all these other things. Even though very often I will say, well, I mean, V star, it sort of has a relationship to VD set, and consequently the minimum voltage that I need across my transistor ought to be somehow related to V star, and then I crank spice and so on and say, well, lo and behold, it's not such bad intuition, right? Okay. You can read all of this yourselves, but just be very careful. Don't get confused about that. Okay, now we pretty much have put things together. We can start designing circuits. And our start is going to be exactly what you got to design for the homework, a simple single transistor common source stage. Okay, so what we want is a common source amplifier. We want, I don't know why I did this. Okay, anyways, I want high gain, right? Whatever. I want a certain bandwidth. Well, the certain bandwidth, that is sort of understandable. My application tells me I need to have a bandwidth of 100 megahertz. And my application also tells me I better drive 5 picofarads at that speed. Okay, so by and large, what I'm saying is that I'm driving 5 picofarads, and then this FU is 100 megahertz. That's frequency, and this is, I guess, gain. And this would be the AV0, and well, sort of kind of take what you get, right? And 100 is probably a little bit optimistic, but we'll see. Okay, so because I said I wanted to have really high gain, and I know already that 0.35 micron isn't going to cut it, and 0.5, well, I had a slide, sort of, certainly it went all the way up to 280, so 0.5 micron might make it, right? So let's try a half micron transistor, so that we have a chance of meeting our gain requirement. Of course, later we're going to build more complicated amplifiers that have more than one transistor, and one transistor is not responsible for giving us all the gain. All right. So, anyways, now of course you need to figure out what circuit parameters all of this stuff translates into, in particular what GM this translates into. Right. So we have GM times VGS. That's our transistor. We have a CGS here. And I guess we also have a bunch of other capacitors. We have an R out here, and we have a CL here. And so this is V out, and this is VI is equal to VGS. And we want to calculate this H of S, and we want to figure out, in particular, where this thing intersects with unity, where we want to know where this is 1. Right? Well, we know at low frequency, this is going to be 100 or something like it, right? Big anyways. And at low frequency also, all the current flows into this resistor here. Ultimately, this drops all the way down to unity, right? And then we get interested in, because then that's FU. Right? So why does this thing suddenly drop all the way from 100 to just unity? Why? What happens to the current? Well, all the current suddenly at higher and higher frequency, like a torrent, flows into CL. Now, because we know this current here didn't change, right? This doesn't change at all over frequency, but suddenly the total current flowing went up by a factor of 100. That means that the current flowing here has got to be 100 times larger, about AV0 times larger than current flowing here. You know what this tells me? It tells me that I can be lazy, and I like to be lazy if I'm still right. I'm going to ignore this little or out there. It just plain simply doesn't matter, right? And so in the frequency range of interest, this or out doesn't matter, and this is, what is it actually? GM over S times CL, right? That's what it is. Yeah, you can write it by inspection. I didn't even look at the circuit anymore. I tried to remember. But we can analyze this very simple. Now it wouldn't be very difficult to analyze this circuit with or out included. But I tell you, it's going to be a bloody disaster if you do not get rid of stuff that doesn't matter for the particular thing that you're actually interested in. So keep that around. On the other hand, of course, we cannot blindly just eliminate components that mess up our calculations, right? That would be a little bit too opportunistic. So, so now from that we can have omega u is equal to GM over CL, right? And because CL is known and omega u is 2 pi f, u is known too, we know what GM is. We can calculate GM. Right? And so that's what I did here. I calculated GM. It's omega u times CL. More soon, please. Okay. So, and 3 some millisiemens, right? And then we also have to somehow choose V star. Now, there are lots of ways on how to choose V star, but and we will talk a little bit about them, and we'll talk a lot about them, right? But we've sort of seen that a couple of 100 millivolts sort of is reasonable, so I picked here 250, right? Then later we say, well, or VDS min really should be very small, and consequently I use a lower value and so on. Right? That depends on design experience, design requirements, and so on. I picked the value here. Okay, this thing here, V star, is equal to 2ID over GM, right? I know what GM is. I know what V star is. I can know what ID is. That's what I do on this line here. Apparently, I need 400 microamps to do that. Okay, fine, great. So, and if it's too much, well, then I'm going to reduce V star. And I know that then I'm going to have a larger CGS. And whoever is driving this thing is perhaps going to give us a little pat and says, well, you know, good approach, but you're not the only one working here, right? So now we have pretty much everything we want, with one exception. We have the channel lengths, we have the GM, we have the V star, we have the ID. What's missing? Well, we need to know the width of the device. What is W? Right? Okay. So now I have to admit, right? When you use the square law model, of course, in the end, somehow you use fitting parameters, right? You use threshold voltage and mobility and Ciox and lambda and stuff like that somehow was measured, right? Well, obviously, we depend on something also that had to be measured, right? Because there ought to be, different technologies are different, so there ought to be some input from the technology. And so this is the input that we are going to use. What I plot here, or actually simulated here, is that on this vertical axis, I show V star for a particular device. Here it's an NMOS device with a particular size, 10 over 0.5. And here then I have ID. Okay. Now, in my example, in my design, I know my V star, it's 250 millivolts because that's what I have picked. Then, that tells me I need 103 microamps. Wait a second. We had said that we had already calculated what current we need. 400 microamps. Well, but that's for a transistor of unknown width W, right? If we use the transistor that had a width of 10 micron, in order to get that V star of 250 millivolts, this chart tells us that we would need 103 micron. Now, in reality, we are going to use 400 microns, so we're going to have to use a wider device, almost 4 times as wide, about 40 micron. And I do the calculation here accurately with 27 digits after the comma, and I get 38 micron. So now I know the width of the device. Now if I want to know CGS, I can figure that out too, and I can figure out what is VDS and so on. If they're too large, then I have to iterate. But I'm not iterating wildly. I do not pick some widths and simulate, and then it doesn't meet my specs, and then I push another button, and now it meets that spec, but the other one is totally off, and so on. I have a design flow. I actually designed this very simple amplifier. Yeah. Okay, so the most important stuff, of course, is these parameters, these device parameters that we came up with, and then to make it work, we will need such graphs here, such graphs that relate V star to ID for a given W over L, and then we just scale the W, right? Okay. Very simple, and that's all you got to do for the homework. So the homework is really super simple. And you don't need additional stuff even that the fab wouldn't give us. So now we have to evaluate, well, did we meet our goals? Well, the first goal, that a little bit more zoom. The first goal is that we have to have a 100 megahertz unity gain bandwidth. I put this now into SPICE, and you know it's written a little bit small there, but I'm so proud of it. I write it now in large. 100.8 megahertz. Okay, this device isn't a square law device, I promise. But we can design the amplifier. This is how fast it needs to be, because that's the whatever WYSIWYG standard, right? And we design it for that, and it just meets, right? That's it. That's what I call design, not pushing buttons. Okay, there's also the phase plot. Then the gain. The gain we can figure out in 2 ways. We can figure it out the wrong way and the right way. Here is first the wrong way. This is, of course, an AC analysis, right? Here is frequency, and here is the magnitude response. Very good to figure out what the unity gain bandwidth is of our amplifier. It's not very good to figure out, or it's at least very tricky to figure out what the gain, what the open loop low frequency gain is of our amplifier. Why is this a misleading and dangerous thing to look at for that? Why? Yeah.
It never actually gets down to 0 hertz.
Well, that wouldn't matter. I mean, we could simulate on linear scale, and it would go down to 0. So actually, in that sense, I mean, this is, if we can go as far as we want, it's not going to change. It's 46 dB here. No, the reason is that, remember, the AV0 of a single transistor, and hence the open loop gain of such an amplifier here, it looks something like this. It depends on where we are. Well, this is not a differential amplifier. If it was a differential amplifier, usually we do the AC response of a differential amplifier for VID equals 0, and usually that corresponds to being somewhere here in the middle, and this is actually symmetrical, and we just have this peak. Well, this peak is a good thing if we want to convince ourselves of what wonderful designers we are. It's not very good if we actually want to get our circuit to work, right? Because in reality, of course, the VDS or Vout, whatever it is, right? It's going to vary, and it's going to vary between this and this point, and consequently the gain, the real gain that we have is this one, and not this one. We still could get, if we wanted, we could get that from an AC analysis, but then we would have to buy a sort transistor so that Vout is this value, not this one here, right? And we can do that, and sometimes we do that, but there are even simpler ways. Well, you know, the gain, AV, there are really two possible definitions for the gain. One of them, the simpler one, is Vout over Vin. And actually, that's the one for an amplifier that usually matters, right? And then there is also the small signal gain where we say, well, you know, if we have an amplifier that doesn't even work for Vn equals 0, like the amplifier that we just designed, right? We have to have at least a threshold voltage on the gate or something like it, right? Then we have this small signal gain. That would be the AV, which would be then dV out dVi, or Vin, right? So both are good gains for an amplifier, especially sort of a diff amp, and so it's usually this thing that matters. For a transistor, this thing is kind of a bizarre thing, and so it's often this thing that matters, or we often specify this thing. And of course, if this lambda story applies, where our out is totally independent of VDS, then these things happen to be equal, and then using this all the time is just fine. And even using this point is just fine, because this lambda story says that we should be getting something like this, right, for gain. But we don't. Okay, so here, now I'm sure we need more zoom again, yeah? Okay, not quite as much the scales are needed. Okay, thanks. So here I have now V out, and here I have the gain AV, and I also have AV, and we know now why they're different. And this one, the red one, this is actually capital AV 0. 0 means just it's at DC, right? And the other one here is the AV0. Okay? Heck, I mean, for once, this is almost anti-Murphy, so something ought to be wrong, right? For once, because this matters and not this one, we actually win, right? This one is a little bit better. Although here the benefit is kind of minimal, right? So again, how much gain do we get? Well, actually this thing goes up to more than 400. The reason that we have this flat top here, of course, is not that the amplifier has such a bizarre gain characteristic, right? I've warned you that stuff like that doesn't happen in physics. But it's simply because I clipped it, because it probably would have gone up. Well, actually it goes up, very often goes up to infinity, because simply because we divide by Vn, and Vn at one point is 0, and then if the amplifier is a little offset at the output, right, 1 microvolt divided by 0 is still infinity. So this goes up too. But the more important stuff is here, right? Here, this line here is for gain 100. This was our target, right? Actually, I didn't remember this. I actually wasn't so crazy when I spec'd a gain of 100. So what this means is we need at least 605 millivolts across our transistor. And because of this impact ionization story, we don't want to have more than 3.6 volts across our transistor. Well, because the supply is less than 3.6 volts, I guess in this case we don't have to worry about this point, and I just put it there to show you the full simulation. Notice that the lowercase AV0 actually would only go up to 2.8 volts, so that would be a problem, but again, most of the time we care about the red stuff, not the blue stuff in this graph. So in a way, of course, depending on how we build the current source, we can go from 600 millivolts to 3 volts or so with this amplifier and maintain a gain of 100. If we wanted only, maybe, well, 300 some millivolts or so across our transistor, which is still larger than V star, right? Then the gain would drop down to something like 25. Right? Okay. It really depends, right? We can get a lot of gain, but we need a lot of voltage. It's very expensive. We don't have that, a lot of voltage. Okay. So now I summarize this thing, and you know, I mean, this is by and large, this is about 90% of this course. From now on, we're going to look at this and turn it around and use it and so on. But if you know this, then you can design, and the rest is kind of easy. So let's summarize this so that we really need to know know how to use this now. So there are a couple of entry points, but one thing that is always a good entry point is GM. Figure out how much GM you need. That is usually something that, and it's a small signal parameter, so we don't depend on ugly large signal equations and so on. And of course, it's very important for the circuit. The L we have to pick, that takes a little bit of experience, but we know short channel gives us high FT. So if something isn't quite fast enough, well, one way to go about it is perhaps to look at whether we could speak lower L. The other thing is that the L, of course, also affects our route, or more significantly AV0, right? If we want more gain, then also maybe we can increase the channel length, right? Of course, if we already have difficulty with meeting speed requirements, well, we know that that is probably not going to solve our problems. We also have to pick a V star, right? And there again, we know that it's not going to be 5 volts. It would be impossible. So a few hundred millivolts is good. And heck, if we really need efficiency, right? Speed isn't that important. Low power is the name of the game. Then we'll try. Maybe we can get by with 120 millivolts, right? Don't make it 50 millivolts, because the transistor is going to work very inefficiently, if you even can get it there, right? Okay. So, and then this has, of course, a whole range of important implications. We talked about all of these. Once you have done all of these, you largely designed our circuit, and surprise, ID just drops out. So when we talk about low power design, it means that we make the right choices here, right? Low power design, just choosing a small ID, well, I mean, give me a break. I can always reduce the supply current. Of course, the circuit's not going to work anymore. Well, big success. Just turn it off. It's even lower supply. And then we need to get W, and for that we need SPICE. And again, the easiest stuff is to run a bunch of simulations for different channel lengths and put them somewhere in your folder, and you will need them all the time for your homeworks. Because in the homeworks, I never give you W and L. I tell you V star, right? And go from there, right? Okay, and the key thing, I guess I'm now sounding like an old gramophone that's stuck. This is the key. So this way we can do design, and the reason is that this approach doesn't depend on the complicated behavior of short channel devices. It works just fine with that. So the next 2 slides, they are such graphs that I have run for I kept the W the same, but I chose different channel lengths, and then again V star here and an ID over there. And so I use those in design. And I have these from here, sort of a bunch of shorter channel length transistors, and here is a bunch of longer channel length transistors, and you can run these yourselves also. Let's use another couple of minutes No, let's skip this. You have enough summary. Otherwise it gets boring and some are already asleep, so I don't want to insist. The what? 39. Sure. Okay. Yes. Yes, yes. Of course, funny thing is that if you tested this circuit, you probably wouldn't use 1 volt because it would go very nonlinear, right? With such a large input, and also with 1 volt, the output. Well, if the gain is 100, the output's going to be 100 volts, and so crazy, right? So, but the reason why we do that is we are in small signal. In small signal, everything is totally proportional. So it doesn't matter. I could test my circuit with 1,000 volts, and then the output would just be 100,000 volts, right? The circuit is linear as soon as we go to on an AC analysis. So it doesn't matter. I really can use here 1 volt just as well as I can use 1 microvolt. And then 1 volt has one very trivial but very convenient advantage, and that is when I want to plot the gain of the circuit, normally all I plot is V out. In reality, I would have to plot V out divided by Vi, which of course I could do, but if Vi is equal to 1 volt, I don't need to do that division. So it kind of is pure laziness why I always, just about all my AC analysis, I use 1 volt. GM and no, see the SPICE internally, it takes this circuit from the netlist that you put in, and then it immediately makes out of it. It makes out of it this thing here, right? So Vi and V out, and consequently then V out is going to be, it then sort of internally writes a numerical expression for V out is GM or O over 1 plus S or O times CL, right? Something like that, right? I think that's the equation that it figures out, right? So times Vi, of course. Now you can put any Vi you want into this equation. You always get a V out that is just larger than Vi by the gain of the circuit. It doesn't matter at all what this Vi was once you are in the small signal domain. You have to be very, very careful. I messed it up now, but there is also a DC equal whatever, a few hundred millivolts. That's the DC bias point. That one you need to be accurate. That's a physical real voltage, because that one is what SPICE is going to use to figure out what GM and or out and all of these things are, right? And of course, if you bias off, then it doesn't work right. But once you are in the AC analysis, that's no longer an issue. Right? So we can safely use a 1 volt there.
How did you pick that range for VGS to sweep from 800 millivolts to 900, just arbitrarily? Your experience?
Well, that I guess is in the next slide, right? Here? Or where is this?
In the circuit schematic on page 39, you mentioned in the DC analysis you sweep VGS from 800 millivolts to 900 millivolts to get a bias point.
Oh, okay. Well, I mean, Well, I know that the threshold voltage of my device is give or take 600 millivolts. The V star is not equal to VD set, but you know, sort of I add that, then I have roughly sort of an idea of the VGS that I would expect. And so about 800 millivolts, right? And then I sweep around that. But I have to be honest. Usually I run it over a fairly large range. Then I figure out where the action is, and then I scale that and run it again. So most likely I actually ran this more than once, and then just zoomed into. And you will also have to do that. Of course, if you have a differential amplifier, then it's easier because you know the offset. It's 0 if you have matched devices, right? But yeah, there is nothing. It's just yeah. This one here. How I make this graph? So first of all, I always make VDS equals to VGS, and the reason is that then GM doesn't really depend a whole lot. GM doesn't depend a whole lot on VDS as long as we are really in a saturation, right? And then in SPICE, I put my device in like that. Diode connected. It's really, I mean, it's a strange circuit. And I drive it with the current ID. Incidentally, I also very often leave, in my diagrams, I very often do not show where this terminal is connected. Well, of course, it's got to be connected somewhere, right? But I know charge conservation, so I know the current is coming from somewhere. So I know. I save my time. I guess circuit designers got to be lazy because there's so much stuff to actually do right and worry about that the stuff that doesn't matter we better ignore. Okay, so then every version of SPICE has its own way to figure out parameters, right? You know it's straightforward to get out ID of a transistor, but just as you can get ID of M1, if this was called M1, you actually can ask SPICE also what is GM of M1 and so on. And then I just plot, use an expression plot. I plot ID versus the expression 2ID over GM. I use the calculator in the post-processor to just plot. Make this the expression used for my x-axis. So. Yeah.
You draw the RO versus the VDS, and you have three curves. One slow and normal and fast. So
Okay.
Slow and fast.
These are these different parameters files. If you look, when you download the SPICE text from the website, you will see that every transistor really has sort of 3 incarnations. The nominal one, that is sort of the average device characteristic that we would be getting back from the fabrication. The fast ones, that would be devices that are kind of pretty far off and tilted towards going extra fast. It's, we briefly talked about that way earlier, I guess, in lecture 2 or 3, 2. Yeah, that is sort of a clunky way to take care of parameter variations that we get, right? So in fact, for design, what we generally will do is we will run our design for checking, at least, using all these 3 different kinds of parameters. Now in homeworks, very often we'll just stick with the nominal and be done with it. But for design, if we actually make a chip, we can't do that, right? We probably would run into troubles. And there is also one design approach that really doesn't work very well, and that is very often when we design a real chip which has to, of course, then work overall, low VDD and high temperature and slow devices and fast devices and nominal devices and so on and so forth. We start designing, setting all the parasitic capacitors to 0, using the nominal device files, using room temperature, using nominal supply voltage. Well, you can almost be guaranteed that when you stick in all the parasitics, when you lower the supply voltage to the minimum that you can deal with, you use the slow or fast parameters, you crank up the temperature to the maximum, 100 degrees C or something like that the IC is still supposed to operate under. Most likely your beautiful design isn't going to work anymore. So very often when we design for a real chip, we actually design for kind of the worst case from the start, right? Okay, the nominal supply voltage is 3.3 volt, but we have plus minus 10%, so we design for 3 volt from the start. It doesn't help us that sometimes we're actually going to get more voltage. Right? And of course, then afterwards, we have to make sure that we don't get horrible impact ionization when we are 10% over at 3.6 volts or something like that. Okay, so that's these three curves are just to sort of show the kind of variation we get on stuff like voltage gain. Now we have just a few more minutes, and I would like to use those to introduce the next topic. And the next topic is electronic noise. And really, why the heck should we care about noise? Right? Noise is close your ears. And there are lots of ways we could say that, but one of them is sort of summarized here. If you can use a little bit more zoom, it will be easier to read. Yeah, sir. Hello, a little bit more zoom here. Yeah. Okay, so signal-to-noise ratio. Well, signal-to-noise ratio is really defined as the ratio of the power of the signal to the power of the noise. And we will derive all of these things. But the power of the signal is more or less right, proportional to VDD square. Right? No big surprise here. The power of the noise, well, apparently it's proportional to temperature. Hot apparently is bad. Boltzmann constant, well, we can look it up in a physics book. And inversely proportional to capacitance. Strange. We'll see why. So if we want to have little noise, apparently we need big C. Okay, now signal-to-noise ratio is the ratio of these. Okay, now let's look at that. Technology scaling means that VDD goes down. While VDD appears in the denominator of this equation with the square. That means that the signal-to-noise ratio goes way down. Right? Of course, we can take care of that by making C big. Very big. Okay? But if we make C big, we're going to need a lot of GM to drive that C at a reasonable speed, and then the power goes up. Right? And so the question is, do these things just compensate one? I mean, we have then also the more efficient short channel technology. Do these things compensate? Or net, is it a win? Net, is it a disadvantage or so? But the point is, well, of course, noise is very important because noise is connected to power. And everybody talks about low power design. Well, talking about this, again, I mean, I just make ideas. Recently, I had to review a paper for a conference, and they said, well, we redesigned our chip and so on to use less power by replacing all the amplifiers by low power amplifiers. It's totally meaningless, right? I mean, either they had gas guzzlers before, in which case they just didn't do the design, right? They probably shouldn't have published the earlier paper. Or then they don't meet the specs anymore, or they changed them anyways, right? It's totally meaningless to talk about low power design unless you really know what your specs are and how to translate these specs into a circuit that realizes and meets those specs with minimum power. And the ticket to doing that is understanding electronic noise. And that's why we're going to spend a few lectures on electronic noise. Okay.